Today we're going to work with MATLAB's built-in function interp1 to perform a few different types of interpolation. And let's see what the example is that we're looking at here. It says you perform a test drive on an automobile where you alternately accelerate the automobile and then hold it at a steady velocity. Note that you never de-accelerate during the experiment. The time series of the spot measurements of velocity can be tabulated as, and here they are. And we're told to do three different things here, and so I guess this first one that we're going to do, linear interpolation, that would be part A. And I'm going to actually have us make 4 different plots, okay, for A, B, C, and D. And we'll go ahead and we'll use the subplot command. So we're going to create a 2x2 grid, and this will be the first entry in that 2x2 grid. All right. Next, let's go ahead and plot T and V. Hold on. And then we want to perform that interpolation. So I want to point out exactly how this function works here first. So we'll do interp1. We'll need to input the data, so T and V. Then we want to specify where we would like to evaluate this thing at. So maybe we'll say we're going to evaluate this at, say, t equals 30. And then the last thing is you want the type of interpolation that you want to do. So first we want linear. Let's go ahead and give this a run, see if we get any errors. We should also see one plot, but we're going to put a second plot on that here in a minute. So there's just our data, and it looks like we got an output from our interpolation function, 20. Now, let's see how we can actually plot something using this. So we just evaluated this at one point. Let's maybe say XX. That's what we'll plug in. So at XX is the variable. And we would like to plot this. So I'm going to use fplot. And so the first thing we have in here is just the function. And the next thing we want is the domain, so 0 to 110. Okay. And that should get that done. Let's take a look. All right, looks great. And then there's 3 more blank spots in here that we're going to fill with figures or with graphs. Right, but of course, you can see that in this specific example, you can see the downside to the linear interpolation. It's that here, this person is always accelerating at a constant over each interval. But maybe that acceleration isn't constant. Let's try out another one. So the next one is supposed to be nearest neighbor. And so this is actually even more simple than the linear interpolation. Right? With linear interpolation, we're just connecting each consecutive pair of points with a line. Here, we will still be connecting them with lines, but what we'll do is we'll just take on the height of the nearest point. Let's see what that looks like. And I'm going to just go ahead and copy and paste this, and we'll make some edits to it. So to make sure that this is using nearest neighbor, then right here I can just replace this with nearest. And we want this to go in the second spot for subplot. And I think now that we have multiple of these, it might help to start titling these. Maybe we'll title this one as linear. We'll title the next one as nearest go ahead and give it a run. There we go. And again, you can see this is taking on the height of the nearest point. So this might be good for maybe discrete changes. Okay. Or maybe it's really important that we have the, or we don't overshoot the y value. All right, let's try the next one. Let's try the cubic spline. So here's the next one, and we'll go ahead and we'll copy and paste, and then we're going to talk about it a little bit after we replace everything we want. So this is no longer nearest, this is the cubic spline. You can just put spline here. And we want this to go in the third location. Okay, and that should get it done. Let's run it and then we'll talk about it. Okay, so you can see it here. We have our cubic now. So what it's doing is it's connecting every pair of points with a cubic. And then you might remember when we did the quadratic interpolation derivation. Right, one of the things we required was that the first derivative be continuous. And this made our graph a little bit smoother. We didn't have these abrupt changes in the derivative. Well, with a cubic, we can go a step further. We actually have both our first and second derivatives are continuous. Okay. And this thing here says not end condition. So let's explain what that is. So at these endpoints here, and looking at these first 2 points and these last 2 points, we're going to require that switch from the first to the second point and the second last to the last. We want to ensure that the third derivative is actually also continuous, which means that the first cubic is the same as the second cubic. So we actually just have one cubic going from point 1 to the third point. And that's why we're calling this not a knot, is because now you can almost imagine like this point here is it's not a knot. Right? But you can see the problem here, right? This shows that the velocity would be decreasing at certain points in time. And we don't want that. We said in this problem that we're never deaccelerating. And that's where this next one will come in handy. The downside to this next one is the second derivative is not necessarily going to be continuous. But again, at least it won't overshoot. And this last one here, we're going to call cubic hermite interpolation. And let me put more piecewise here too. All right, and to compute this last one, we are again going to copy and paste and just make a couple edits. So we want this to go in the fourth entry of our subplot. This time we want to be using what we're going to call p-chip. P-chip will use the piecewise cubic hermite interpolation. P-chip. And here I will just write hermite. We'll give it a run. All right, and we can see this last one doesn't have that overshooting issue. But again, the downside is it's not quite as smooth, but again, at least it's not overshooting. And is what I'd like us to do next, okay, is try and use interp2, which will be used for 3D interpolation. Okay, so some of you might remember this problem here from the homework. We had two variables that were independent variables, D and S, okay, diameter, slope, and then Q here was the flow. That was our dependent variable. And what we had done with it is we actually linearized it, and then we performed multiple linear regression, and then we just converted back, right, to be in terms of the original variables. And actually, I think we can suppress some of this stuff now because we're less interested in it. Okay, that looks good. And the only other thing here is now we're going to try and answer this next question. But we're going to use both our results from up here and from interpolation. But notice D, S, and Q are written a little bit different here. Notice that if we look up at our original data, right, you have 0.3, 0.6, and 0.9 are the only D values that we're actually using, and S we only have 0.001, 0.01, and 0.05. Okay, so there's not very many options there. And what I want you to do is we want to try and write this in that mesh grid format that we usually use when we do 3D plots. Okay. And so the way to do that is the first input, you can make those values go vertically. And then for the next variable, you can make those values run horizontally, which you can see we have happening here. And then from there, we wanted to put in the corresponding Q value. So I had to look at my original data and say, hey, when D is 0.3 and S is 0.01, what is Q? And say when D is 0.6 and S is 0.01, what is Q? And it was 0.82. So now that we got that all filled out, now we can actually use interp2. D, S, Q, and then both of the values that we want to evaluate this at, so 0.1 and 0.01. And then lastly, we need to put in here either spline or linear. This thing's actually curved, so I think spline is going to be a better estimate, but maybe we'll try out both. Let's say flow spline, and then we'll try the same thing with linear. Go ahead and give it a run. Actually, if we want to take a look at the graph for a second to remind ourselves what it looked like, this was our data with those red asterisks, and then we fit it with this surface here. All right, and so that means we could have also estimated our answer here graphically. But let's see what we got here. I just need to move up my command window a little bit. So we have two pretty close numbers. Let's see what we would have got had we used our model that we created in the homework here. So I'm going to just copy this. I'll make some edits to it. So this here, let's maybe say flow, and then instead of spline or linear, let's put in here regression. How about that? Right, and we still have A stored, so we don't need to change those. But maybe we should go here and write in what D and S are. So D is equal to 0.5. We said, and S is equal to 0.01. And I suppressed it. Let me fix that. All right, there we go. And they're all pretty close. The linear seems to be the one that's furthest from the other two, which is kind of expected. Again, it was a curved surface. But that is it for interp1 and interp2.